Have you ever wondered how your phone knows you tilted it, or how a simple security alarm can tell when someone taps on the window? Well, today we're going to pull back the curtain on that little piece of magic. We're going to break down, step by step, how a physical shake gets turned into a digital signal that a computer can actually understand.
It really all boils down to one big question, right? How do we teach a machine to feel something? How does a circuit know it's been shaken, or a smart gadget know it's been tapped? We need some kind of bridge that connects the physical world of bumps and shakes to the digital world of ones and zeros.
And believe it or not, that bridge often looks just like this. Say hello to the KY002-Vibration sensor. This little component is the hero of our story today. The best way to think of it is like a digital nerve ending. It has one and only one job: to feel a vibration and report back. So, how in the world does this tiny thing work? You might be picturing some complex microchip doing all the heavy lifting, but the real secret here is beautifully simple and completely mechanical. Let's pop the hood and take a look inside.
Okay, when you get right down to it, the mechanism inside is almost laughably basic. There are just two key parts. You've got a conductive outer casing, and then, hanging right in the middle of it, is this super delicate, also conductive, spring. And that's it. Seriously, the entire function of this sensor depends on how these two simple parts interact. So let's break down the action. When it's just sitting there, completely still, we call that the at-rest state. The spring isn't touching the casing at all. There's a tiny air gap, which creates what we call an open circuit. Basically, electricity can't flow. Think of it like a light switch that's turned off. But the moment a vibration hits it, that spring wobbles and tap, it makes contact with the casing. For just a split second, that closes the circuit and the switch is on.
A perfect analogy for this is just a regular old doorbell. When no one is pushing the button, the circuit is open and the bell is quiet. A vibration is just like a finger coming along and pressing that button. It momentarily closes the circuit and ding-dong, it sends a signal. It's that simple.
Okay, so we've got a mechanical switch flipping on and off. That's pretty cool, but how does that simple physical action become a clean digital message that a computer can read? Well, for that, we have to follow the electricity.
In digital electronics, we don't really think in terms of on and off. We think in voltage levels, high and low. And this sensor uses a really clever trick. Its normal resting state is held at a high voltage. But when that vibration makes the spring touch the casing, the voltage on the signal line gets yanked all the way down to low. And that sudden drop, that transition from high to low, that is the signal. That's the moment of detection. But you might be wondering, why is the signal high in the first place? Well, that's thanks to an unsung hero in electronics called a pull-up resistor. The best way to think about it is like a spring on a screen door. Without that spring, the door might just flop around in the breeze, and you wouldn't know if it was really open or closed. In electronics, that's called a floating signal, and it causes all sorts of problems. The pull-up resistor is like that spring. It firmly holds the signal high until a real vibration gives it a strong push to pull it low. This little guy is absolutely key to preventing false alarms.
Okay, so our sensor is creating this nice, clean, high to low signal. Awesome. But a signal is pretty useless without a brain to actually interpret it. And that, my friends, is where the microcontroller and a little bit of code come into play.
Now, it's really important to separate these two roles. The KY002 sensor, that's the sense organ. Its only job is to feel the vibration. But the Arduino, or any microcontroller really, that's the brain. It's the part that reads the signal from the sensor and then, based on the code we upload to it, decides what to do next. And connecting these two is incredibly easy. It's just a simple 3-wire setup. The plus pin hooks up to power, that gives the sensor its energy. The minus pin goes to ground, which you need to complete any electrical circuit. And then the S pin, that's for signal. This is the communication line where the sensor speaks to the Arduino's brain, sending that high or low voltage.
Now for the intelligence part, the code. This is what brings the whole circuit to life, and it's basically built in two parts. First, you've got the setup function. Think of this as the preparation phase. It only runs one time, right when you power it on. And second, you've got the loop function, which is the active part that runs over and over and over again forever. So let's look at setup real quick. First, we tell the Arduino, hey, I need you to listen for the sensor on pin 10. Then comes this really crucial line, digital write, vibe high. Remember that pull-up resistor we talked about? This little line of code actually activates the one that's built right into the Arduino, which is super convenient for keeping our signal stable. And finally, serial.begin just opens up a communication channel to our computer. And that's it.
The Arduino is all prepped and ready to listen. Once setup is done, the loop function just takes over in this relentless cycle. First, digital read vibe checks the voltage coming from the sensor. Then, the if statement asks a very simple question: is the value low? If the answer is yes, then it executes the code inside the brackets. In this case, just printing a message. If the answer is no, it just loops back to the beginning and checks again. And this check happens thousands of times every single second. And here it is, the result of all that work. What you're looking at is the serial monitor, just a little text window from our computer. And check it out. Every single time the sensor gets a little tap or shake, the Arduino's loop detects that low signal and bam, it prints signal detected. We have officially translated a physical event into digital information. How cool is that?
So we've gone through the whole process, from the physical shake all the way to the digital message on the screen. Now let's put it all together and talk about why understanding this one simple component is actually so powerful.
So let's recap that entire journey real quick. It starts with a physical shake. That triggers a mechanical action, the spring closing the switch. That in turn creates an electrical signal as the voltage drops to low. Then the Arduino's code interprets that signal, which finally leads to our visible output on the screen. From a real-world shake to a digital message, the journey is complete.
So why does any of this matter? Because this fundamental principle is the key to countless real-world applications. You could use this to build a simple but really effective security alarm for a window. In an industrial setting, it could monitor machinery for weird vibrations that might signal a failure is coming. You could even use it in sports and fitness to measure shocks and impacts to analyze an athlete's performance.
So there you have it. What started as just a simple shake has been translated into a clear, actionable digital signal. You now understand the mechanics, the electronics, and the logic that makes it all happen. The only question left is, what are you going to build with it?